Hi friends, today our topic is Winkler Batch formula. This Winkler Batch formula is associated with bending of beams which are initially curved. There are beams which are initially curved which has a lot of application. Example, a crane hook. We all know the crane hook is used to lift heavy objects. While lifting, stress is imparted onto the hook. Compressive stress as well as tensile stress can be generated in the crane hook as per the application or type of loading. In this case, simple bending equation M by I is equal to E by R is equal to F by Y cannot be used. So we have to derive an expression for the stress, and that's called Winkler Batch formula applied to the initially curved beams. Now we have some assumptions. These assumptions are very important. The transverse section which are plane before bending remains plane after bending. Hooke's law is applicable. Stress by strain is equal to elasticity. Each layer of beam is free to expand or contract. Modulus of elasticity in tension is equal to modulus of elasticity in compression. These are the assumptions and they may ask for 2 marks. The transverse section rotates about an axis called neutral axis. In order to get the resultant normal force 0, neutral axis will get shifted to the center of curvature by a distance E from the centroidal axis, and this distance is called eccentricity. Now here we have a beam which is initially curved. Here phi is the angle of curvature. Rn shown in the lavender color, it is the neutral axis. The transverse section rotates about neutral axis. We already said that. This is the radius of curvature or centroid, and this R is the radius of curvature of section. In order to derive an expression for the stress, we have to consider a small strip here over the radius of curvature of section. The thickness of the section is dy. Distance of this section or radius of curvature of section from the neutral axis is y, and eccentricity is E. This is the centroidal axis RC. It is represented as R bar also. When the beam is getting rotated, this phi changes to delta phi. For getting an expression for the stress generated in the beam, we have the length, initial length of the material. Angle is equal to arc by radius. From that, arc length is equal to phi into Rn minus y. Rn is the neutral axis. This y distance, if we subtract, we will get the R. This is the initial arch length. Therefore, L is equal to Rn minus y into phi. After loading, angle of rotation is delta phi. Change in angle is delta phi. Change in dimension is equal to minus y into delta phi as the neutral axis gets shifted. We can consider Rn is equal to 0. Now we can calculate the strain. Strain is equal to change in dimension by original dimension. Divide this by this. Stress is equal to strain into epsilon from the Hooke's law. We will get an expression for the stress. Yes, now we have an expression for the stress, and we already said that while loading the neutral axis gets shifted, and now we want to find out the position of the neutral axis now. And to find out the position of the neutral axis, we need to consider the forces and we need to bring the forces into equilibrium. Now we have the expression for the stress. I said stress multiplied by the area will give the force. And now getting the forces into equilibrium, we have force is equal to integral over the area A into stress into dA. This is the equation for force. Getting it into equilibrium equal to 0. Put the value of stress we already obtained. Stress is equal to Ey delta phi by Rn minus y into phi, because we already derived it here. Now you can easily follow the steps. In the next step, I added an Rn and subtracted an Rn. It is shown here. Multiply with a negative on the LHS and RHS. Rearrange this. Put the integral inside. Set it into different terms. Bring one term to the right side. We will get an expression for A. From this we can bring the position of neutral axis R suffix n. Here Rn minus y is equal to R. This is radius of curvature of the section. We can go to the geometry to check Rn minus y. This is Rn, this is y. Rn minus y will give the R. As we said in the beginning that simple bending equation is not applicable, we have to calculate the moment in order to find the stress acting on the hook or the initially curved beam. Therefore, we are considering the moment. Moment is equal to force into distance. Force into distance. Force is equal to stress multiplied by area, sigma dA, into y. This means that we are considering the moment. Force into distance. This will give the moment over the area A. Substitute the value of sigma and substitute for y also. Now we have substituted for stress. We will get the equation E delta phi by phi integral of the area A y square dA by Rn minus y. From the geometry y is equal to Rn minus R. Substituting the value of y and Rn minus y. For this y we give substitution, and for this Rn minus y we have to give substitution. Then it will reduce to this form. Put integral inside. This equation, integral over the area A, Rn square R by dA, this can be converted. From the equation 1, we already seen that integral over the area A, dA by R is equal to A by Rn. This is the first area moment of inertia. This is, the result of this is area multiplied by y bar. And for solving that, we will get Rn square into A by Rn. A by Rn instead of integral over the area A, dA by R. A into R bar. R bar is the centroidal axis distance. And by solving, we will get this form. E delta phi by phi is equal to m by A into R bar minus Rn. Geometry R bar minus Rn is equal to E. Therefore, E delta phi by phi is equal to m divided by A. But we already have sigma is equal to E delta phi by phi into y by Rn minus y. From that, we will get sigma is equal to m by A into y by R. And this is the derivation for Winkler-Bach formula. In the next section, we will apply it into a rectangular section. Thank you.